Welcome to the Explainer. So, if you've ever felt totally intimidated by the heavy math of physics, well, you're in exactly the right place. Today, we're taking the engine of everything, thermodynamics, and we're going to make it beautifully simple. Our goal here is to completely demystify all those complex equations. How? Just by looking at simple, real-world interactions of heat and movement. Let's get right into it.
Here's our quick roadmap for today. First, a welcome to thermodynamics. Then, the 3 types of energy. After that, doing work with gas, the first law, applying the math, and finally, we'll wrap up with the second law.
Section 1, welcome to thermodynamics.
Okay, so thermodynamics is basically the study of energy relationships involving heat, mechanical work, and energy transfer. The absolute crucial point I want you to take away here is that this entire field, seriously, no matter how complex the engine or the system you're looking at is, literally boils down to just 3 interacting physical elements. We're talking heat, mechanical work, and how energy transfers between them. It's not magic, it's just mechanics.
Section 2, 3 types of energy. Now, what's really interesting about this is just how incredibly simple it actually is. To understand any thermodynamic system, you really just need to track 3 main players. You've got heat, which we just call Q. You've got internal energy, represented as delta U. And finally, work, which is W. Honestly, that's the whole shebang. Just keep your eyes on those 3 interacting pieces, and the entire puzzle falls right into place.
Section 3, doing work with gas.
Let's look at what work actually looks like in the real world. Imagine a gas getting hot and expanding. As it expands, it literally pushes out on its boundary surfaces, like it physically forces a piston outward. That mechanical action right there, moving the boundary, that is exactly what we mean when we say doing positive work. To keep things super simple, we just contrast 2 basic scenarios here. First, think of a gas expanding. Its volume goes up and it pushes the piston out. That's work done by the system, which gives us a positive W. Now flip it. Imagine some external force pushing that piston back in, really compressing the gas down so the volume decreases. That's work done on the system, which gives us a negative W. Make sense, right?
And mathematically speaking, this physical push is honestly just basic arithmetic. The work equation is simply W equals P times delta V. Or, in plain English, the work done equals the constant pressure of the gas multiplied by the change in its volume. So you're literally just measuring how hard the gas is pushing out, multiplied by how far it pushes. See? The math isn't scary at all.
Section 4, the first law. All right, here's the big one. Delta U equals Q minus W, the first law of thermodynamics. Now think of this as the universe's ultimate accounting system. Energy is always perfectly conserved. All this means is that the change in the internal energy trapped inside a closed system is just equal to the heat, the fire you add to it, minus the mechanical pushing the system does. Now, this little cheat sheet is basically your master key for all those plus and minus signs. Getting the math right is really as simple as knowing 2 things. Is heat going in or out, and is the gas pushing out or being squeezed? Like, if heat is added, Q is positive. If the gas expands and does work by the system, W is positive. Just keep these concepts in your mind and you honestly can't go wrong.
Section 5, applying the math.
Okay, let's put this together with a real-world example, just to prove how intuitive this is. Say a gas expands from 0.4 to 0.7 cubic meters at a constant pressure, and we toss in 140 kilojoules of heat. Step 1, figure out the mechanical work the gas did by expanding. We just multiply our pressure by our volume change, which gives us 60 kilojoules of work. Step 2, find the internal energy change. We take the total heat we added, that's 140 kilojoules, and simply subtract the 60 kilojoules of work the gas did. And boom, we get a final internal energy increase of 80 kilojoules. We literally just subtracted the work from the heat to find exactly how much energy stayed trapped inside the gas. Pretty easy, right?
Section 6, the second law.
Now, the first law tells us energy is perfectly conserved, but the second law introduces a simple, undeniable reality. Heat is basically a one-way street. Spontaneous heat flow is always from a high-temperature object to a low-temperature object, never the reverse. Think about it. You leave a hot cup of coffee in a cold room, and the heat flows out into the room. Sadly, unless you have some sort of magical mug, that room is never going to spontaneously pump heat back into your coffee to warm it up. And that actually leaves us with this really wild final thought. If energy is perfectly conserved in the universe, just like the first law proves, why can't a cold object spontaneously heat up a warm one? I mean, mathematically, it wouldn't violate the conservation of energy, yet it literally never happens. I want you to just ponder that profound little cliffhanger about the irreversible nature of time and physics. Thanks so much for joining this explainer today. I really hope this leaves you curious to learn more about the strict, fascinating laws that govern our universe.